Okay, good morning. This is Physics with Keith. I think this is the third session we've done. It is Saturday, it's 10 o'clock in the morning, so let's do some physics tuition. I've got loaded on my second screen here the live chat stream for YouTube, so when you have questions or if you've got anything you want to answer, I ask a question, you want to give an answer. If you pop your answer in or your question in there, then I'll be able to see it. There's only a 7-second delay between me saying something and you hearing it, so there won't be too much of an awkward pause. It looks like right now we have 2 people viewing live according to the list, so well done to you 2 for turning up, and hopefully maybe a few more will turn up a bit later. If you do know any one of your friends or something that that you know would benefit from this, do let them know to tune in now, and then they can get that benefit as well. So just to see if anyone wants to interact, if you want to put a little comment just saying hello or something, you don't have to, but if you want to, then I'll be able to see on my screen and see if anyone is actually out there. Now, I have had a question or a broad topic that was asked that I was asked if I could go through, and I'm happy to do that. Remember, you can ask me to go through whatever you want me to go through at GCSE or A level. I'm happy to do that for you, and I can ask you questions and you can answer them, or you can answer them in your head, or you can answer out loud, or you can type your answers. The topic was energy. Well, there was 2 topics really. One was energy transfers and the other was energy resources, and they are 2 very different topics. So what I thought for a plan for this morning, I thought we would do this. So let's just see if that scene transition worked. Yeah, that looks like it worked. So this is what I thought we would do. Looking at energy transfers first, which is work done, energy stores. Well, you can read that list there yourself. And then moving on to energy resources at the very end. Keeping the 2 as separate as I can, because it is easy to get the 2 mixed up, and that's a problem. So let us start with energy transfers. Another name for transferring energy is doing work. So that would be work done. And there's an equation. And I said a couple of weeks ago, the best way to get good at remembering equations is to use equations. And so the equation for work done, I'll just write this underneath here, and I'll use a W for work done, is your force multiplied by your displacement. And I'll use a D for displacement at the moment because I'm pitching this for GCSE level, but if you're an A-level student watching this, then feel free to use an S. Good morning. We've already had a comment come through. Good morning to you. So these 2 things here, force and displacement, are vectors. It's important that you remember that. What is a vector? It is a quantity that carries with it a direction. So this is a vector, which is force, and this is a vector, which is displacement. But this thing over here, which is the amount of work we have done, which is another name for the amount of energy we've transferred, that thing over there is not a vector. It's a scalar. Okay, so if we've got a vector times a vector equals a scalar, how does that work? Well, it's a particular type of multiplication. If you're an A-level student, feel free to look up scalar multiplication, also known as dot product, and that's why I've used a dot as the multiplication symbol here. If you're at GCSE level and you've ever noticed that sometimes you see a dot for multiplication, and maybe it's not very well explained why, this is why. It's a particular type of multiplication where you multiply 2 vectors together and get a scalar out. In other words, the direction seems to disappear. Energy doesn't have a direction. So work done doesn't have a direction. But force does. You push in a particular direction. And displacement does. Things move in a particular direction a certain distance. And that's what our displacement is. So here's our equation. What does that mean? What it means for GCSE students is that the displacement and the force must be in the same direction for work to be done. So let me give you an example. If I scroll down a tiny bit, give myself a bit more room. Imagine I have a ball. Here's a ball. Let's try and make it circular. There we are. Here's a ball. And let's imagine that I push it. Well, before I push it, it has no kinetic energy because it's not moving. Let's imagine that's the situation. So my ball is sat on a surface, it's not moving, ergo it has no kinetic energy. Let's draw that surface. There it is. Now let's imagine I push it. Now if I just give it an instantaneous sudden push and then stop pushing it, then what I've done is pushed it for a small amount of time. There's no way I can apply a force for 0 seconds. If I push it, I've pushed it for a small amount of time. And so while I was pushing it, and this is, in fact, I'm going to use different colours for this. Let's use red for our force arrow. So while I was pushing it in this direction, it was gaining kinetic energy. It was starting to move. And the distance it moved whilst I was pushing it, and I'll use a blue arrow for this, so the distance it moved whilst I was pushing it from here to, well, however far it went, could have been here. That distance it moved whilst I was pushing it, that multiplied by the force I pushed it with is the amount of energy I gave this ball, the amount of kinetic energy I gave this ball. Kinetic energy is energy associated with motion. So there's, oh, I've labelled the wrong one. Here's the distance over which it is moved, and remember that that has to be a displacement in the same direction as the force, but we're going to keep it simple and just talk about distance. As long as everything's in the same direction, we'll keep it simple. Here's the force that I push it with. Now once I've stopped pushing it, so we've got to the end of that distance d, I stopped pushing it, it's still moving, it still has that energy, it still has that kinetic energy. So why would it eventually slow down and stop rolling? It would eventually slow down and stop rolling because there's another force acting on it. And the other force acting on it is the air resistance, or any sort of frictional force. Air resistance is a frictional force. And that force is going to be acting on it in the opposite direction. And this is some sort of frictional force or air resistance. And this frictional force or air resistance is going to be acting on it. Let's just move this out of the screen so I can animate this. As this is moving in this direction, slowing down, slowing down, slowing down and stopping, that force, that resistive force, multiplied by the distance is the amount of energy that's being taken away from the ball. So it's the kinetic energy being taken away from the ball. So the principle here is that if the force and displacement are in the same direction, if this and this are the same direction, then this increases, or this is positive. We give the ball energy. But if the displacement and the force are in opposite directions, remember you can watch this back later and pause it if you want to make notes from this. So if these are in the opposite direction, then for reasons that A-level physicists will learn when they learn about dot products, the work done is negative. In other words, we're taking energy away from the ball. So that's the principle of work done. Now there's a lovely example I like to give which really causes some difficulties with some students, which is let's draw the picture. Let's imagine you're a waiter. Let's scroll down a bit. Let's imagine you're a waiter or a waitress. Here you are. Here's your legs. Here's one hand, and here's the other hand holding a tray. And upon that tray is a drink. Okay? And you are walking across the busy restaurant floor. And you're walking in this direction across the busy restaurant floor. And the drink is not getting any higher and it's not getting any lower. And you're walking at a constant speed. So how much work is being done on that drink? And the answer is none. Because there are no forces trying to make the drink go faster or slower in the direction parallel to the direction that the drink is moving. So the drink itself is moving horizontally in the direction of the blue arrow, and there aren't any forces in the direction of the red arrow, forwards or backwards, because it's moving at a constant speed. It's not accelerating. it's not decelerating. Remember, force is equal to mass multiplied by acceleration. If our acceleration is 0, then our resultant force is 0. So if there's no resultant force on this drink, in this liquid, in the horizontal direction, and the vertical direction, we're just looking in the horizontal, then no work is done. It doesn't get any faster, it doesn't get any slower, the kinetic energy stays the same. So even though we've got a displacement of the drink, which in this case is horizontal, and we could have a question asked in an exam where we have the weight of the drink. Well, that's a force, isn't it? The weight of the drink is a force, and we've got a distance that the drink moves, and we think, oh, okay, so work done, I've got to multiply those together. No, we don't, because they're perpendicular. And so because those two vectors are perpendicular, no work is actually being done on this drink. If the waitress lifted the drink up, then as she accelerates that drink, so it initially has no vertical velocity, as she accelerates it so it gains vertical velocity, it's increasing its kinetic energy. And so work is being done on it. And that's because it's being displaced in the same or in the opposite direction, so up or down, compared to the weight, which is down. So that's work done. It is a bit complicated. Please don't forget you can ask me questions. I've just spent 11 minutes powering through the equation work done is force multiplied by displacement. It is actually quite a tricky equation. So what I'll do, I'll ask you a question, and I'll give you a little bit of time to come up with the answer. I'll ask you a couple of questions actually. I'll give you a bit of time to come up with the answer, and you can type your answer in. Let's see if you've sort of understood what's going on. So let's start with an easy question. Let's say I've got a surface here, I've got a block here. Let's imagine the surface has no friction. There's no friction on this surface at all. Let's say that the block is pushed from the left with 10 newtons. And it starts to move, and it continues moving, and so it gets faster and faster and faster. And let's say that I stop pushing the block after it has travelled a distance of 10 centimetres. So the question is, how much work have I done on that block? Or in other words, how much kinetic energy have I given that block? So you've got 7 seconds delay, and then you can type the answer. So I'll try to pick numbers that you could use in your head. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. See if an answer appears. No answers are appearing. Long, protracted, awkward pause. Okay, it's possible you've typed an answer, but there's because of the 7-second delay. I'm going to talk anyway. If you haven't, then join in. Do type an answer. Let's do the maths together. Work done is force multiplied by displacement. Our force is 10 newtons. Our displacement, we're not going to use 10 here. We're going to be very careful. In physics, we don't use centimetres as a unit very often. When we do maths questions, we don't use it at all. So 10 centimetres is 0.10 metres. And so 10 multiplied by 0.10 is 1. And the unit of work done, which is the unit of energy, because that's what we're doing, we're giving it energy, is 1 joule. So that's 1 joule. Okay, that was a pretty straightforward one. Let's make it a little bit more complicated. Let's imagine now that as I push it, there is a frictional force acting in the opposite direction. The frictional force acting in this direction, oops, that was a badly drawn arrow. I might as well try it again. And I've accidentally erased part of my J from joule. There we go. So let's imagine I have a frictional force acting in the opposite direction of 5 newtons. Let's imagine it's a constant frictional force. I'm pushing with 10 newtons. There's a 5 newton frictional force, and As I push it, it travels a distance of 10 centimeters, and the displacement is the same direction as the resultant force. So, what do you think the work done will be? So 7 seconds. Let's see if we can work it out. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Yep, exactly right, half a joule. The resultant force is half as much, and therefore the work done is half as much. Absolutely perfect. Right, let's make it a little bit more complicated, because at GCSE level things do get a little bit more complicated. Let's imagine that now we are pushing, our block up a ramp. So here's my ramp, here's my ball, and as I push it up the ramp, the ball itself, I'm going to tell you what its mass is. The mass of the ball is 1 kilogram. Let's keep it nice and simple. Let's imagine that I push it up the ramp with a force of, I don't know, 30 newtons, let's say. There's no friction, and I push it a distance in the direction of the ramp. I push it a distance of, let's say 1 meter. Again, let's keep the numbers simple. And let's say the angle of the ramp, because we'll need the angle of the ramp now to make this make sense. Let's say the angle of the ramp. This is the more difficult end of the questions you'll get at GCSE level. You could get a question like this at GCSE level, but it'll be towards the end of the paper. So let's imagine the angle of the ramp is, let's say 30 degrees. Okay, you may need a calculator. What I'd like to know is how much work is done. Just work it out myself. What's that? No answers yet? Okay, let me give you a clue. There are 2 ways of solving this. The first way is to either resolve this force, this 30 Newton force, and this displacement, so that we are looking horizontally, and that way the weight goes away, because remember, work done uses force multiplied by displacement, but the force and displacement must be parallel. So if we resolve these so that they're horizontal, then the vertical component, the weight, goes away. And if you're thinking, what is he talking about? I'm talking about resolving vectors. And if you've not done that, then this isn't going to make a lot of sense, and it's something you might want to let me know so we can go into resolving vectors. Maybe not this session where we're focusing on energy, but maybe the next session. The alternative is to resolve the weight into 2 components, and that's going to take a little bit less work. So that's the version I'm going to do. Pun not intended. So we have weight acting down, and the weight of this, let's call it 10 newtons because it's 1 kilogram. Now that 10 Newton down, I could describe as 2 vectors added together. And I'll use an orange colour for these 2 components of that weight. I've got a component that is perpendicular to the ramp. I'm not interested in that. And a component that is parallel to the ramp. Now I am interested in that. And the angle here is going to be 30 degrees. And so I can use my trigonometry, the fact that the weight here is 10 newtons, and the fact that this angle is 30 degrees, this angle here is 30 degrees, I could use that to find out what this component, the opposite component to the angle, is. And I do that using SOHCAHTOA. So I know that if 10 newtons is the hypotenuse, 10 multiplied by the sine of 30 degrees is this component there. Now, as that's in the opposite direction to the 30 newtons I'm pushing with, my resultant force is going to be 30 minus that 10 sine. I think I might have gone off the screen here, so I'll move this. So double check and see if I've gone off the screen. No, I'm just on the screen. That's okay. So that's my resultant force, and my displacement is 1 meter. So my work done is going to be that force, so 30 minus 10 sine 30 degrees multiplied by my displacement, which is just 1 meter, and so that gives me a work done. I'm going to have to come down here to write it out. I'll take my calculator out again because I've forgotten what it was. 30 sine 10 times 30 plus, and that gives me, okay, 25 joules. I may have made a mistake, of course. Please do check. I do make mistakes. Did I need a calculator to work that out? Sine of 30. It's one of those that you're supposed to remember. Sine of 30. Let's check I'm not being a moron. No, I am right. Sine of 30 is a half. So half times 10 is 5. So work our way from inside to outside. I knew I picked these numbers for a reason. Sine of 30 is a half. Half times 10 is 5. 5 away from 30 is 25. 25 times 1 is 25. So the work done is 25 joules. Okay, if that spooked you and scared you, please remember that this is towards the end of your GCSE paper. This is the most difficult question about work done you're going to get, where you end up having to resolve vectors as well into components in order to calculate the work done. They could ask you a question like that, but they would be jolly unkind if they did. Well, examiners can be unkind. So that's work done covered, and it only took 22 minutes. So let's move on to energy stores. When we do work, we move energy from one store to another. We call that energy transfer. And there are a few energy stores you have to remember. Now, old textbooks and old resources may refer to these as energy types. Well, that terminology has fallen out of fashion because there really aren't different types of energy. But energy is stored in different ways. And there's a list. And you can find these lists in textbooks, or you can just Google it online. But the energy stores are things like Kinetic. Is that on the screen? Let's just have a little look. Yeah, that's just about on the screen. Things like kinetic energy. Get my pen again. So kinetic energy, gravitational potential energy. Never just call it gravity, ever. Gravitational potential energy. And then we've got elastic potential energy. What else have we got? I suppose we've got heat, which is energy transferred through well, thermal energy, I suppose we could call it. So heat, it's a type of energy. What energy store? What else have we got? I suppose we could have nuclear potential energy, but we're certainly not going to talk about that. Can you think of any others that I've forgotten? Comment now and see if there's any others I've forgotten. I'm sure they're all very important, but I've no doubt there are others. The things that are not energy stores often get described. Friction. Nope, nope, nope. That's a force. And it's related to work done through the equation that you can see at the bottom of the screen there, but it is not an energy store. Or push, pull, twist, all those sorts of things. Air resistance, buoyancy. None of these are energy stores. Now the four big energy stores that you'll be using at GCSE level are listed there. And there are equations that we use to calculate how much energy is in each of those stores. And I'll list them now, and the bad news is you just got to remember them. 1 second, this appears to have conked out. There we are, it's working again. Right, yes, the bad news is you just have to remember them. So let's start with kinetic energy. The kinetic energy store, the equation for that is 1/2 multiplied by mass of a body multiplied by the square of the speed of the body. Now, I'm just going to check that's on the screen. Yeah, that's on the screen. Okay, so that, I can derive that for you if you want, just from the equation work done is force times displacement, or you can do it in terms of a graph of momentum multiplied by speed. And if you take the area of a graph, which would be a straight line in this case, the area of the line underneath momentum speed would actually be that equation. But you're not asked to derive that equation in your GCSE, so maybe we should just focus on the bits you are asked to do. If you're interested, though, you can derive that using a graph. Okay, what else have we got? We've got gravitational potential energy, and that is mgh. And if you look at the equation mgh, m times g is the weight of a body, that's a force, and h is how far it's been moved up from the ground, so that's a displacement. So what you've got there is a force multiplied by a displacement, which is work done. So that equation is exactly the same as force times displacement. We've got elastic potential energy, which is your half k E squared. Now, many exam boards actually give you this equation. They give you this one, but they don't give you this one. So you have to remember the top one. Check with your exam board whether you are given the bottom one. If you are, then because the top equation, kinetic energy, is almost the same as the bottom equation for elastic potential energy, you can usually remind yourself of the top equation by glancing at the bottom one. It can be quite helpful mnemonic to remember. They're in the same sort of form. So let's just delete these silly smiley faces and stuff. There we go. And the final equation, which is for heat, I suppose we could call it, thermal energy store, that is mc, and I'll use a T here, where T is absolute temperature measured in Kelvin. And if you're not sure what Kelvin are, or you're not familiar with that equation, or you don't know what I'm talking about, because you haven't covered heat yet, it's not usually done within the same topic as heat, but here we go. Now, if I have a body, let's say I lift some mass up. Here, oops, let's say here's my mass, and I'm going to lift it up. As I lift it up through a certain distance, I gift it potential energy. I am increasing its gravitational potential energy. So let's draw the ground. Here it is. And let's lift this body up. And if I lift this body up, so it's raised in height by that much. Let's draw a second line. Let's do it in green. It's now raised in height by that much. Call that height h. Then I've given it an energy m times g times h. The mass of this is m, and g, depending on your GCSE, most exam boards use 10 newtons per kilogram. AQA uses 9.8 newtons per kilogram. You might not be happy with that notation. Hang on. And if you're doing A-level physics, it's 9.81 newtons per kilogram. So do check with your exam board whether you use 10 or 9.8. It will be in their specification. It will also be written on the front or inside their exam papers, past papers, so do double check. And unfortunately, it does actually matter, because if you use the wrong one, you might end up losing the marks. Examiners mark some questions, but some questions are marked automatically by computer. So just be careful of that. And that's for all exam boards. So this mass, which has been lifted up, if I go the height has been lifted up, multiplied by the m, multiplied by g, which is 10 or 9.8, that gives me the energy that I've stored within that mass. If I let go of that mass, it falls. That amount of energy that's stored as gravitational potential energy stops being gravitational potential energy and starts being transferred into the kinetic energy store. It gets faster until just before it hits the ground. Now obviously once it's hit the ground it stops, and that energy then dissipates as heat. But before it stopped, that instant before it stopped, the gravitational potential energy that was stored has all been passed across into the kinetic energy store. So in other words, the mgh that was stored is now equal to the half mv squared it has just before it hits the ground. Now if you look at that equation closely, you'll see that the mass of the body is on both sides of the equation. So we can cancel it out. And rearranging this equation, multiply through by 2, so 2gh equals v squared. And then I'm just going to write it the other way around because I want my v on the left. And then taking the square root of this equation, so the square root of v squared is just v. I get an equation that I can use to calculate what the speed of the body will be when it hits the ground. Okay. That's a common sort of question you're asked as well. So that's energy stores covered. Please do ask me questions. Remember, this is a live tutorial session. I've been at it for half an hour, but I at least want to tick off the first 4 points because that's what I was asked to do. And if I've got time, I might move on to energy resources very quickly at the end. I've got a few nice simulations to show you for that. But it is interactive, so you should ask, or you should say, yes, I get it, or you should say, no, I don't understand, do it again, or, you know, interact with me. So let's talk about energy transfer diagrams. There's 2 types of energy transfer diagrams. There's these types of energy transfer diagrams, kinetic energy with an arrow to gravitational potential energy, and sometimes you'll see it with the force that does the work written on the arrow. So in this case, kinetic energy is reducing, gravitational potential energy is increasing as Serena Williams throws the ball in the air. The ball, once it's left her hand, is not being pushed by her hand anymore. But the weight of the ball down is slowing it down as it ascends. So the higher the ball gets, the slower it gets. Therefore, it's losing kinetic energy. But because it's getting higher, it's gaining gravitational potential energy. The force that's taking away the kinetic energy and putting it in gravitational potential energy, that force is the force of gravity. So sometimes you'll see this with an arrow and the word gravity over the arrow. Here's, I don't know who that is on the other side of that custard pie. Looks like Theresa May or something, but okay, here's a custard pie. Kinetic energy, the pie is moving, eventually the pie stops moving. So where does that energy go? Believe it or not, it's dissipated as thermal energy. And Feynman gives a lovely introduction to his lectures, the Feynman lecture books, in which he talks about thermal energy and how it is that it's stored. Heat energy, you might know that when something gets hotter, the molecules within it vibrate more. They vibrate quicker, the frequency of vibration increases, everything vibrates more. There's more motion of the molecules within the substance. And so Feynman likes to describe it like this. He says that when an object is moving, dropping, you've got this very organized motion. Everything's moving in the average movement is all in the same direction. So a very organized motion of this body. Now when it hits the ground, thud, and eventually stops moving, the motion is all still there, but it's gone from a nice organized motion of everything moving in the same direction to a very disorganized motion of everything shaking and vibrating around within the substance. It's heated up. And that's what happens here. I always quite liked that, the idea that the motion doesn't actually go anywhere. Feynman gives another little description of the sun and how it gives energy to things on Earth. Because of course in the sun we've got nuclear fusion reactions taking place, fusing hydrogen, forming helium and releasing tremendous amounts of energy. And we can see that. It's pumping out light and heat, and we can see that from the sun. And so a long time ago there were plants, and those plants photosynthesized, and they took that energy, that fire from the sun, took that energy and they locked it away in glucose or whatever it is that they make in photosynthesis. I'm not a biologist, C6H12O6 or something. Then they take that and those plants die, and maybe they get fossilized, and you dig it out the ground and you've got a lump of coal. Then you stick it on your barbecue and you ignite it and fire comes out. And what's coming out is chemical energy, which is then being transferred into the heat energy store. Ah, there we are, chemical energy. There's another energy store. So the fire you get out is the energy, well, what you see is manifesting, it's revealing the energy that originally came from the sun. It's as though we've captured the fire from the sun and released it from the coal. I mean, if it's not, that's the case. Fire isn't a substance, but it's quite a nice way of visualizing this this idea that energy is conserved and it's just passed around. So these sorts of energy transfer diagrams, here's one that's got several stages to it. Chemical potential energy in the fuel, we ignite it. Thermal energy, everything heats up. That causes the gas to move more quickly, so we gain kinetic energy, and that kinetic energy then gets transferred to gravitational potential energy as it rises due to gravitational force that we're moving against. So some of these diagrams have, some of these energy transfer diagrams have a few stages to them. But there's another type of energy transfer diagram which is called a Sankey diagram. And Sankey diagrams, I'm going to do my best to sketch some now. Sankey diagrams are special because they give you an idea of the proportion of energy that's being transferred. And the classic example is an old filament light bulb. So if you imagine I've got a filament light bulb, and the energy that's going into that filament light bulb is electrical energy. There we are, there's another store of energy. Electrical energy. And maybe it's 100 joules that goes into this light bulb. Within a certain amount of time, I'm watching it. Maybe I'm watching it for a second, and in that second, 100 joules of energy goes into it. Well, in a Sankey diagram, the width of the arrows is proportional to the amount of energy. So let's make my arrow 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares wide. Much easier to do these on squared paper. So here's going to be my arrow head at the other end, and here's the beginning of my arrow. Oopsie. Let's go back to my straight line drawing tool. You would have a ruler, of course. Now, on a light bulb, the useful form of energy that we like having is light. Unfortunately, in the old filament lamps, they weren't that efficient. So let's imagine that 90% of the energy was wasted. So this was 10% efficient. If that's the case, then our arrow is going to, there we go, is going to be, the useful energy arrow at the end is going to be a tenth as wide. Really struggling to draw them with this tool because everything's on top of each other, but I think I'm getting there. Okay, there we go. So this arrow here is light energy. There we are, that's another energy store, light. And there's only 10 joules here. There's only 10 joules because it's 10% efficient. And where's the other 90% gone? Well, they've come off. And there's different ways of drawing this. And I'm afraid I'm not much of an artist, especially not when I'm writing on a screen with no screen on it and looking at a different screen. So bear with me if this looks terrible. And any physics teachers that are watching this and saying, oh my god, what's he drawing? I'm doing my best. Okay, so, yeah, what am I doing? Let's try that again. Like that, and we're going to have a nice smooth curve. You don't have to do a nice smooth curve, but I'm going for it. Let's... Oh, that was tragic. Okay, now this arrow that's come off has to be 9 squares wide. So 1, 2, 3, 4, 5, 6, 7, 8, 9 squares wide. So that's about yay wide. Let's finish off our arrowhead. The size of the arrowhead doesn't matter. It's all about the width of the arrow that matters. Still no questions coming in. Okay. So I did my best to draw these curves, and they're not wonderful, but they're okay. So this here is my heat energy, and there's going to be 90 joules of energy there. And you'll notice in terms of arrowheads, this arrowhead here is 10 squares wide. This one here is only 9 squares wide, if I've counted them right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, this one's only 1 square wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, so I've counted it all correctly. So the arrow width is proportional to the amount of energy represented by that arrow. Now, Sankey diagrams like this are useful for visually seeing the efficiency of an appliance, or of a transducer. A transducer is a component that transfers energy from one store to another. Transducer. So in this case, the transducer is a light bulb or a filament lamp. And the width of the arrow is what matters. So you can at a glance see what the efficiency is. In this case, the efficiency of this lamp is going to be the 10 joules we put in, the 10 joules that's useful that we get out, divided by the 100 joules we get in. Efficiency is what's useful out, divided by what you put in. That is actually an equation that I think you get given, but it's not bad to remember it anyway. It's not too bad. Wasted energy is the total in minus the useful. Okay, so there's another type of Sankey diagram. You don't just have to have energy on Sankey diagrams, you can also have power, which is energy divided by time. So this is 100 watts, then this would be 10 watts, and this would be 90 watts. And what is power? Power is the work done in a certain amount of time. So that's Sankey diagrams. You can get Sankey diagrams that can look a lot more sophisticated. Let me show you with the power of Google. See if I can load up a new window. Sankey diagram. Images. Yeah, so if we just go onto Google and have a look at images of Sankey diagrams, you'll see exactly what I mean. We've got this here is that's for education. Here's a different sort of Sankey diagram that might not be for energy. I've seen Sankey diagrams for financial systems. Sankey diagram, this is an asset Sankey diagram, so I guess that's financial. But they all, this is energy flow, so this is a Sankey diagram for energy, but they all share the same property, which is that the width of the arrow represents the proportion of the energy or the power. Hello, I'm being given an advert, get rid of you. The energy or the power share that is represented by that bit of the arrow. And people like making Sankey diagrams all smooth and aesthetically pleasing, but they really don't have to be. You could do Sankey diagrams like this, where there's multiple stages, or you could do, so let's just show you what I meant. Sankey diagrams like this, so there's multiple stages. You could do Sankey diagrams with nice right angles if you're not so good at drawing the curves, which clearly I'm not. So as long as the width of the arrow is proportional, then your Sankey diagram is fine. Let's just move that because you couldn't see that properly. There we go. Okay, so that was energy transfer diagrams. They're the easy ones that just say one energy store, the energy is passed to another energy store. Sankey diagrams, that's width of the arrow matters. So last few minutes, let's just talk about energy resources. So once you've got, let's add to this list here, what else did we have? We had electrical. What else did we have here? Light. Suppose we could put sound here. That's pushing it a little bit, I suppose. Light, sound. Were there any others that came up? No. Okay, that's done. So energy resources. Don't get them mixed up with this list. This list is energy stores. Energy resources is completely different. Unfortunately, in every textbook I've ever seen, energy resources and energy get plonked together in the same chapter, usually in a chapter quite close to forces, which means you end up getting forces and energy resources all mixed up in your head, and I can understand why that might happen. But this is a list of energy stores. Energy resources are things that you can use to usually generate electricity. That's not the only way, but to generate electricity is the main use of energy resources. So here's a website, and you can see the URL at the top there. This is gridwatchtemplar.co.uk. I have no affiliation with them whatsoever. And as you can see on this website, we've got some dials and some charts. Now, I loaded this website earlier on. It says 1040, so it's only recently refreshed. But if I press refresh, I can get the... Oh, it might be the most recent data. Yeah, every 10 minutes or so it does refresh, though. And it shows you what's happening in the national grid. For example, it shows you the frequency of AC on the national grid. And you can see on this that the frequency is chemical. Yes, thank you. I've just noticed there's a comment for chemical, and I hadn't put it on the list. Thank you. Chemical. Well done, thank you. Right, let's go back to that list again. Sorry. Let's go back to this. So, frequency, that's the frequency of AC, which is about 50 hertz in the UK. Over here we've got the demand. It's in billions of watts, gigawatts. That might be a bit small for you to see on this screen, but you can zoom it in when you go to this website yourself. And so right now we are demanding nearly 25 billion watts. That means every second the UK wants 25 billion joules of electrical energy. That is a huge amount. Now, if we look over here, there are different energy resources. There's this thing here, which is gas, type of gas turbine, which I'll show you a little simulation of. There's nuclear, which I think you saw a schematic of a nuclear reactor last time. There's biomass, burning things that grow, trees and mould and I don't know what, burning stuff. There's wind. The wind turbines are spinning up. It's quite a windy day at the moment in the UK, so nearly 36% of our power is being generated currently from wind. In fact, we are generating more power currently from wind than we are from nuclear power stations. You go back 10 years and people were saying there's no way renewable fuels will ever be able to take out to meet our demands. But let's just consider this for a second. More than a third of our electricity usage is being generated with wind. So if we turned a third of our electrical appliances off nationally, would we need any of the others? Now, it's quite a simplistic approach, and obviously wind is unreliable because if it's not blowing we can't generate as much, so we can't just get rid of all non-renewable energy resources, but it's quite a big proportion. It does make you think. So I'm just throwing words around here. Let's drill down into those words a little bit. Renewable. Things like biomass, wind, they are renewable because within the span of human existence they're not going to run out. Trees can be planted, they can grow, they'll die, we can chop them down and we can burn them. Or biomass often comes from discarded food waste, for example, that you use to ferment and make methane gas, which we can burn as well. So biomass is renewable. As long as there are humans alive, we can keep making it. Wind is renewable. As long as there are humans alive, the wind will continue to blow. And there are others. Solar is renewable because the sun will shine for as long as humans are alive. This little dial here is solar. Currently is actually not bad. It says on percentage that's about 20% is solar. So let's just think about that. 20% solar, 35% wind. That's half of our energy usage right now can be provided with just wind and the sun. Turn off half of our electrical appliances. Now, the non-renewable, we've also got, I think, 1% from hydro. That's big dams, which is not very much. At the moment, we're sending electrical energy to France and to to the Netherlands, sorry, but we are borrowing a bit from Ireland. So the national grid, we also have a electrical grid that goes beyond our national grid, and we can take energy from other places and give it back to them later on, depending on demand. Adds a bit of flexibility. The other dials here, nuclear, for example, this is non-renewable. Nuclear energy, as you know, we dig uranium out the ground, we stick it in a nuclear reactor, but once we've run out of uranium, we're not going to have any more. It's not regenerated at a rate where it's not regenerated now at all. So we will run out of uranium within the span of human existence. We could run out of uranium in the span of human existence, so it's non-renewable. But it's quite handy because it doesn't produce greenhouse gases, so it's quite a clean energy resource, and we need it to provide a baseline for when the wind isn't blowing or when the sun isn't shining. We then can have the nuclear energy pick up the slack. And we've got this thing here called CCGT. They're gas turbines. Now, gas is a really good energy resource because we can very quickly turn it up and turn it down. So if the demand increases, we can very quickly increase that demand by burning more gas. Problem is, it does produce CO2, which contributes to global warming. So let's have a little look at some of these energy resources. Let's start with coal and oil. Very unpopular in the UK, a lot more popular in other parts of the world. Very, very simple system. Burn oil or burn coal. It's not quite like this. You powder the coal so it burns faster. But basically, yes, you put coal or oil into your thermal power station. It's called a thermal power station because we burn things to make them hot. That then heats water, which boils, producing steam, which you use to drive a turbine. So the steam goes pumping through the turbine, and it's the turbine spinning that generates the electrical energy, which transfers the kinetic energy from the steam into the electrical energy. And what we can do is we can let more steam out, and you can see the power output goes up. We can let less steam out, and the power output goes down. But if we don't let enough steam out, the pressure increases. So we have to decrease the amount of fuel we put in to cool down this inside the power station so that the pressure doesn't increase so much. So in power stations, you're always looking at the demand, trying to balance the output with the demand. And with coal power stations, it's so hot in here, you can't quickly heat and cool it down. It takes a bit of time to heat and cool it down. Although nowhere near as much time as nuclear. Nuclear power stations take a much longer time to fire up or cool down. Weeks. So you can't quickly respond to demand. So what this thing here is the steam then needs to turn back into water so we can put it back into the I keep wanting to call it reactor, but it's not. Into the power station core here, and so we have this big cooling tower that cools the steam to make it into water. And sometimes you'll see steam pouring out the top, and that's what's happening. So that's coal power and oil power. Gas, which is this. This is your gas power. This works in a slightly different way. Well, it's very similar, slightly different though. The design is slightly different, but basically you've got these turbines, which are just basically big propellers that spin around, and to make them spin, we have to get something moving through it very fast. But rather than having water through these, you just use air. And so as you heat it up by putting more gas in there, and you heat it up and heat it up and heat it up and heat it up, this acts like a giant jet engine pulling more air through, and as that air gets pulled through, it spins up these turbines. And you can see how quickly I was able to spin that up. So here we can see the demand is dropping, so I can very quickly drop my supply down by dropping the gas pressure to cool down the inside, and try to match my I've overshot it, there we are, and tried to match my supply with my demand. If the demand suddenly spikes, I can spin this up and increase my supply. So that's gas. The other non-renewable, there's one more non-renewable here, which is your nuclear reactor. We've looked at nuclear reactors already last time. But with nuclear reactors, the idea is that we use a radioactive source. Not radioactive source, you can do, but they're not very good. We use nuclear fission of uranium-235, so pull the control rods out, get that thing fissioning, and the uranium-235 gets hot as it splits into two daughter nuclei, and the hot water, which we use, in this case water as a moderator as well as a coolant, will then via a heat exchanger heat up a secondary circuit. This particular design doesn't seem to have a tertiary circuit, which is dangerous, and then you drive a turbine. So it's very, very similar to the coal and oil version. if you look there, heat water, turn turbine, except we use uranium to heat the water. Then we've got our other resources. Let's not do that one yet. We've got geothermal. So a geothermal, this is a renewable resource. And this is only in places where you've got some tectonic activity. So you've got the Earth's crust is quite thin, the rocks underground, a bit closer to the mantle, so they're a bit hotter. And if we pump some water, gravity can do the hard work for us, pump some water down into the hot rocks, the water heats up and turns into steam. And so by letting that steam pass through a turbine, we can generate electricity. The other thing we can do is, because this water is, it's not that dirty, it's only been pumped down into some rocks, and because it's hot water, we can use that to provide heating to towns and villages. And this is done in Iceland, so you can get hot water without having to burn more gas in your boiler or whatever. So that's renewable, because the Earth's mantle will be hot for as long as humans will be alive. And then if we go down here, we've got hydroelectric. Now this is very very reliable, but we don't use it very much for generating electricity unless there's a big demand. So if demand suddenly peaks, we can open the sluice gate here and let loads of water pump through this turbine. But you look what happens to our reservoir starts emptying. And the lower the height of the reservoir, the less force of the water, because there's less weight of water behind it, the less force pushing the water through this turbine, so the turbine doesn't quite spin as fast. And eventually, we don't have enough water anymore. Oh no, we've run out of water. So what do? We have to wait till it rains again to fill up our reservoir. Now, one thing you can do is pump water back up into this when you've got an excess of energy in the national grid. Rather than just wasting it, we can pump water up and use this like a gravitational potential energy battery. We can then empty this when we need it in high demand and pump it back up when we've got, middle of the night when no one's using very much electricity. So that's hydroelectric. Solar, there's different types of solar. This one here is your solar that doesn't heat water. So this is just solar panels, and you want to point the solar panels so that they're pointing at the sun to get maximum area. If they're like this, you get very little energy if you look at the graph. So ideally they'd track the sun across the sky, but they don't actually have to. So the solar panels aren't so good when it's cloudy, obviously, and they're no good in the winter, or not as good in the winter. These are called photovoltaic cells. Photovoltaic cells. If an examiner talks about solar panels, they might be talking about photovoltaic cells like this, or they might be talking about solar panels like this, like the panel on the roof here, where we pump cold water up into the solar panel on the roof. The sun heats up the water, and then we have water that comes out of our tap nice and hot in the house. So this system's getting more and more common in the UK. It doesn't generate electrical energy. What it does is it heats the water directly from the sun. So that's also called a solar panel. So if the examiner wants you to talk about solar panels, just read the question really carefully and think to yourself, are they asking me about photovoltaic cells? Photo as in photograph, light. Photovoltaic as in voltage generating a potential difference, and cell as in the thing that provides electrical energy. There's another type of solar energy which I don't have a simulation for, where mirrors focus the sun on a place where there's water, a little vessel of water. Water's pumped up, then the water heats up, turns to steam, drives a turbine. Exactly the same as with every other form of thermal power station, but the water's heated with the sun instead. We've got wind. Here it is, our wind turbine, and this one, rather than having to heat water to make steam to rush through the turbine's just pushed by the wind. Otherwise, it's basically the same. But if the wind gets too strong, we have to turn these off, tilt the blades so they don't spin, otherwise it will fall apart. If the wind isn't strong enough, they don't work, so it's not very reliable. But it is renewable. And then finally, we've got tidal and wave. Wave energy, very, very rarely used. In the sea, where you've got salt water, this is horrible conditions, lots of corrosion. But basically, wherever I've got motion, I can stick a turbine to generate electrical energy, and that's what this does. It just doesn't generate very much. And lastly, tidal. When the tide comes in, the water rushes through the turbine in one direction. When the tide goes out, the water rushes through the turbine in the other direction, and we can use that to generate electrical energy. Not so good for fishers though. Sort of acts like a giant blender and chews them up. And that's energy resources. I managed to get that done in about 15 minutes, I think. Maybe a little bit longer than I wanted to, but never mind. If there are any questions, now's the time to ask, although you've been at this for an hour now, so you're probably feeling a little bit tired. I'll wait a few seconds, and then if there are no questions, I will call it a day. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi. Okay, there's only 7 Mississippis delay and there's no questions, so I think we'll call that a day. Thank you for the 2 viewers who are still with us, and if you let me know in advance what you want me to cover, very happy to cover it. No problem with that. We'll be doing this again next Saturday. Just get the date here. Next Saturday is the 30th of May. So we're doing it again next Saturday. Tell your friends, tell your family, tell everyone that needs to know about this. Like and subscribe. Here we are, cliche time. Like and subscribe. Has that made the little like and subscribe button come up? No, there it is. Like and subscribe. Share it with your friends. Make sure as many people can benefit from this as possible. And remember that this is interactive. It's supposed to be interactive. You can join in. You can ask questions in real time. Okay. Thank you very much. Stay safe.